Multivariable differentiation. This is differentiation of functions that depend on more than one variable. For example, a function from two variables to the real numbers f of xy equals that. Functions to R are maybe the most commonly appearing functions in applications. Here's the graph of the function plotted with the formula minus 0.2x squared minus 0.06y squared plus 5. The concept of differentiation is just the same as in the one-dimensional case that we saw already. It becomes only a bit more interesting since we can move in more than one direction. The function that is shown here looks very nice and smooth. No jumps, no kinks. No jumps means that the function is continuous. We already looked at multivariable functions for continuity. I hope you remember. A function is continuous in a point of its domain, so here xy, if no matter how I approach the point, the function values also approach the value f of xy. For getting our hands on approaching, we introduced limits. For a function to be differentiable, we saw that it should be continuous, but also not have kinks. This was the limit of the slope of the secant existed and was the same coming from either side. In graphical thinking, we could attach a tangent line to each point of the graph. If you can't remember, please look in the lecture notes of differentiation in one variable. Now let's generalize all of that we know to higher dimensions. First, what is a differential? So that is, what is the derivative of the function? And what is the object that corresponds to a tangent? In 1D, the derivative in a point gave us the slope of the tangent to the graph of the function in this point. This was how much do I go up, respectively down, if I move along the tangent line. If we ask now, how much do I go up or down, it depends on two things. First, on the point where I stand, obviously. So for this example, let's say we stand in P with the coordinates x is -1 and y is -3. And second, how much I go up or down will depend on the direction I move towards. In the one variable situation, we didn't have a choice of direction, but now life becomes richer. What do humans do if they encounter a difficult new situation? They usually assume it's just as simple as before. That can bring one into trouble, but not in our case. So first let's pretend the function was in one variable only, for example in x. That is the cut of the surface for y equal -3 and the graph is shown in red. Here we know exactly what to do. The differential of f of x and y in the point P in x direction is the limit for h towards 0 of f in the coordinate x of our point plus a little bit going in x direction, so plus h. The y coordinate stays the same, so yp minus the function value in our point divided by h. The derivatives that we get if we restrict our function to only varying the variables, so here x and y, are called partial derivatives. And these are written with such a del, such a curly d. So here we write del divided by del x f of xp yp for the derivative in x direction, or a capital D x for the direction, f in the point xp yp. Calculating the partial derivative for each point in x direction, so we keep y fixed but unknown fixed. We only have to differentiate as this was a function in one variable, so only the term in x, that is 0.2 x squared. Everything else is a constant and doesn't impact the derivative. And we get what's written below the picture. The partial derivative in x direction of f of xy is minus 0.4 x. In our black dot indicated point with the coordinates -1, -3, we therefore get minus 0.4 times -1, where -1 is the x coordinate plugged into the derivative, and that is 0.4. Our partial derivative here happens to not depend on y, could, but here it doesn't, and so we don't need the -3. If the original function had a term, for example, x times y, then the derivative in x direction would still have a y in there, and then we would need it, but not here. You can see in the picture very small, but a little red bar that goes from the red dotted line to the tangent. and that would be the 0.4 that you go up on the tangent line if you move from our 0.1 length to the right. This is exactly as in our one-dimensional case, the slope of this tangent to our red dotted curve. In y direction, this is exactly the same. The partial derivative in any point of our function is obtained by keeping the x value fixed. That is, the partial derivative in our example is del f by del y equals minus 2.0.06y, and that is minus 0.12y. Again, if the function was different, there might be an x still in there. And at the point minus 1, minus 3, the partial derivative in y direction is 0.36, which we get by taking the y value of our point as a y in the derivative. So this is if moving on the tangent that is attached to the function f in y direction, we get 0.36 up if we move distance 1 in y direction. What about other directions? For example, in the purple direction where the arrow in the xy plane points to. The direction is, for example, given by the vector v with coordinates 1 and 2. We follow the same idea. We restrict the function. But now, if we move a tiny step of length a into v direction, h times the x coordinate of v is added in the x component, and h times the y coordinate of v is added in the y component. Same definition as before, and we could compute this limit. But there is an easier way to get a directional derivative on the next slides. There is one more formula describing the directional derivative with a t. It says, if we start from our point and walk along the purple line, we go through the points with x coordinates xp, the x coordinate of our point, plus t vp, vp the x coordinate of our direction, and y coordinates yp plus t yv. This is, we have described our line as a function g of t. The partial derivative of f in v direction is then the derivative of the function f of g of t. This is how to get the one variable restriction of the function by parametrizing the purple line as the function g of t. The chain rule for differentiation, which works pretty much the same as in the one-dimensional case, but you might want to read about that in the book. It's not exam relevant though, says that the derivatives are equal. I won't use this description again, and you only need what comes on the following slides for directional derivatives for the exam, but this is another good way of thinking about them. Now we have the directional derivative defined as this limit, and we can go and compute it, but in general that's a bit annoying. So there's a better way of doing that. Namely, remember that differentiation is a linear approximation. The partial derivatives are in one variable, and the corresponding tangent lines are drawn in red for x and green for y, respectively. These two tangent lines span a plane, and this plane is called the tangent plane to the graph f in our point. To each f of x, y, we can attach such a tangent plane. Now the nice thing is that all tangents to the function in this point lie in this tangent plane. If you want to prove that, you have to use the description of directional derivatives by the parametrization, and then you use the chain rule to show that the tangent of any path on the surface that goes through the point f of x, y lies in the tangent plane function. You can find this proof in the book, but let's rather see how a directional derivative relates to the partial derivative, and that is as follows. First, we take a vector v as a vector in the purple direction. This vector is split into the x and y direction. And we know how much a function changes in x and y direction. So in v direction, we have a mixture. The change in x direction is weighted by the x coordinate of v, and the change in y direction is weighted by the y coordinate of v. The directional derivative is vx times del f by del x plus vy times L df by dy. This is what every hiker in the mountains knows. If the steepness in two linearly independent directions, so such as to the right and to the front of me, we immediately know how steep it is to go into any other direction. Curvy mountain roads use that. They don't go directly uphill, but the horizontal component makes them less steep. This is exactly linearity. The slope can be decomposed. And that is great for computations, because we only need to know the partial derivatives and the coordinates of a vector with length 1 in our direction, and we have a formula to get its directional derivative. A comment: why does a vector need to have the length 1? That is because a twice as long vector would give us a factor 2 in the derivative formula. And that is correct. The slope is how much the tangent changes after one step. So when computing directional derivatives, always remember to first normalize the vector that gives the direction. Here the computation is written out for the directional derivative along our purple line. First, we normalize the 1, 2 vector. That is, we get its length as the x-coordinate square plus the y-coordinate square and the square root of it, which is square root of 5. And then we divide the vector by this length to make it length 1. This is v equals 1 divided by square root of 5, 2 divided by square root of 5. And now the directional derivative in this direction is 1 divided by square root of 5 for the x coordinate times the partial derivative in x direction plus its y coordinate times the partial derivative in y direction, and with the values for that we computed already in the point xp, which was -1, -3, we get something that is close to a half. On the bottom of the page you see another way of writing the sum that gives the directional derivative, namely as a scalar product. This is what is written in these two edged brackets. And the scalar product of two vectors is the product of their x-coordinates plus the product of their y-coordinates. That's exactly the formula that we have here. The vector with the partial derivatives as its entries has its own name. It's called the gradient of f, and it is abbreviated by this on the point standing triangle. This is called nabla f. Here you can just see it as an abbreviation, but it also has a nice and important geometric meaning that we see in the following.